Hello, welcome to Aircraft Maintenance Practices Unit 1 lecture. This lesson, we will determine the grain direction needed, identify the minimum bend radius, calculate the bend allowance and setbacks. There will be a practical which require a flat pattern layout to form a given bracket. As we know, aluminum alloys are widely used in the construction of aircraft structure. They may come in the form of rod or cast. The 4-digit system series identify the type of alloy found in the aluminum. 1000 series states that it's a pure 99% aluminum. 2000 series, the main alloy for aluminum will be copper. 3000 series, the main alloy in the aluminum is manganese. 4000, silicon. 5000, magnesium. 6000, silicon and magnesium. 7000 series, the main alloy will be zinc. Factors to consider when we design and bend a sheet metal part. Grain direction. It will be best to bend across the grain than along the grain. Quality of cut. Make sure that all edges are burr removed. Minimum bend radius. This is one of the important factors. Do not bend smaller than the permissible minimum bend radius. So, what is minimum bend radius? It is the smallest inside radius. It can be bent without cracking at the outer heel of the bend is shown here. Using this table provided, let's say the alloy and its temper condition is 2024-T6. Now, what does the 2024, the first digit 2, tells us? If you were to recap back earlier, the 4-digit systems, the first digit 2 represent 2000 series. The main alloy in this case is copper, right? So now 2024-T6 and the material thickness to bend is 0.016 inch, which is 0.41 mm thick. We know that the minimum bend radius required will be 2 times the thickness to 4 times the thickness. That means the minimum bend radius to be used to bend will be minimum of 0.032 inch radius to 0.064 inch radius. All right. So let's recap. Minimum bend radius is limited by the material properties, that is the hardness and thickness, the required bend angle. In this case, from this diagram, the bend angle is 90 degrees. The length of the bend, that is, this is the length of the bend. Condition of cut edge perpendicular to the bend edge, that is to deeper or burrs from the edges. Last, the orientation of bend with respect to the direction of rolling. That means the grain direction. We should bend along the grain direction than across. Just to take note, this is the bend radius that we are referring to, and it's based on the material thickness. Like earlier example, 2 times the material thickness to 4 times the material thickness. Bending stresses. When a metal bends, it will experience various stresses. On the metal outside as shown here, when it bends, the outside area here will experience tensile stress where it will stretch, while the inner material here will experience compressive stress because it will be compressed and squeezed. You see this neutral axis, This is the axis that are in the center of the thickness, equal distance, where along this region, the axis, it will experience zero stress. That means there's no change in length before and after the bend. So normally, what type of failure will occur when improper bending condition was not observed? Surface crack and wrinkling of the inner surface. So when there's a fracture on the outside, it's a tensile failure. Compression failure will have wrinkle effect. Bend allowance. What is bend allowance? It is the length of a sheet metal required to make a bend over the given inside radius, which is the bend radius. In this case, Ri here represent the inside bend radius. The cyan region here is the bend allowance as shown. So in this case, as shown in the slide here, the bend angle required is 90 degrees. So we're given a sheet metal flat plate. We are supposed to calculate the bend allowance, all right? And the red region here represent the distance of the bend allowance required. And with a proper marking out and bending skill, you will be able to achieve the required L1 length, all right, and the correct bend allowance. One thing to take note is the thickness here to consider will be 0.445 to 0.5 times the thickness. What do you mean by that? Given the bend allowance equation shown here, there are three unknown factors. A itself represents the bend angle required. In this case, 90 degrees. So we have a 90 over 360, which is a circle, times 2 times pi. And we inside the bracket itself, there's a Ri and a T. Ri represents the bend radius used or identified, while the thickness will be 0.5 times or 0.045 times the thickness, or it can be in between. All right. Further later, we will have example or samples to do the calculation. You better understand what we mean by that. Right. Bend allowance table. Over a period of times, continuous calculation and usage, people realize that some of the digits are repeating. What do you mean by that? Now, if you were to look at the left side of the columns, there is a material thickness. So these are provided by the manufacturer of the aluminum sheets, and they are available in this thickness range of 0.032 inch thick. The next size available will be 0.040 inch. So in this case, if you require a 0.039, there's no such thickness available in market. The available size is 0.032, 0.040, 0.051, and so on and so forth. So it's quite a consistent, repetitious thickness. And this is the bend radius across the row. All right, so a bend radius can be a 1/16 inch radius, 1/8 inch, 3/16, and quarter, and so on and so forth. So now let's use this table as a guide and find out the required bend angles if the material thickness is 0.051 with available quarter-inch radius quarter-inch bend radius, sorry, and the required bend angle is 90 degrees. So from here, you just go down and look at it. Do you see a 0.428? Yep, this is 90 degrees. So if you want to bend a sheet metal of thickness 0.051 with a quarter-inch radius, the bend allowance is 0.428. Right. We're maintaining the same thickness. If let's say instead of using a quarter, the available bend radius on the pen and box bending machine is 3/16. In this case, you realize that the band allowance is slightly shorter, 0.331 inch. Then if it's a half-inch radius, which is quite big, half-inch band radius, then you realize that maintaining the same thickness material to be bent, my band allowance will be 0.821 shown here. So you do realize that the band allowance will actually variable component, which you will fluctuate with the band radius used. Now, coming back to this, we know that 0.428 is 90-degree band allowance. So what is the number highlighted in red here in this case? Below the 0.428. The number highlighted in red, which is 0.004756 inches, is actually a degree. Okay, a degree in bend. In other words, if let's say you have a 0.051 inch thickness, still the same radius, you want to bend this sheet metal at 60 degree instead of 90, 60 degree. So what we will do is you get this 0.004756 multiplied by 60 degree. You will get the bend allowance required. So this is the bend allowance per degree, a degree in that case. So if it's 45, you just multiply by 45. So you can see how the system works here. Right. And of course, as per the slide here, if you were to multiply 90 to 0.004756, your calculator will show 0.4280, which is in inches. Setback. Setback is another important measurement to know so that we know where does the bend tangent line start. Setback is the distance from the bend tangent line to the mold point, where the mold point is the point of intersection of the lines extending from the outside surface. So over here, this is the bend tangential line or the bend tangent line. So when you bend a material, you have two bend tangent lines in this case. So if you were to have a flat piece, all right, this will be the one in red will be my bend allowance. So how do I know where to start to draw the line? All right, so most important thing is you must calculate your setback in this case so that you know that your first tangential line will be the overall length minus away the setback will give you the start line in this case, for example, the first line here. So the distance is actually the overall length needed minus away the setback, in this case over here the setback. Then you will get the measurement and start to draw the first bend tangent line. All right, setback is used as a sideline during setup for bending, which we will explain later. Used to calculate the flat leg of a bent part and also to determine the developed length, in this case L2 or L1. Right, so let's move on to the next slide, where there are some more examples to talk about setback and bend allowance. One of the factors to consider when carry out bending is the spring back effect. When we bend the material or the metal, it fall into elastic zone where the metal is stressed to below its elastic limit. In this case, the tension side of the material will contract and the compression side will expand, and this results in the spring back. So when we calculate the flat patterns on the sheet metal, one of the value that consider the spring back effect will be K value. From here, we know that the setback is equal to K, okay, times the open bracket bend radius plus thickness. So the K value is given in the table where various angle of bend required. In this case, if let's say you want to bend a 45-degree angle, your K value will be 0.41421. So substitute in this formula, K itself is 0.41421 multiplied by radius, bend radius I identified, and the material thickness. This will give you the setback. further down, there will be example for you to understand better in this case. And you do realize that if the sheet metal were to be bent at 90-degree angle, it will be K will be 1. All right. So on and so forth. So it depends on the bend angle will determine the K value, where we'll also consider in the the spring back effect. Right, this is one of the examples we talk about. Quickly run through it. The material thickness in this case is 0.064 inch. The band radius which we're going to use is 0.25 inch. Do take note, all these measurements will be in imperial unit. Right, so I want to calculate my setback in this case. So to calculate my setback, I know that it is the band radius plus thickness times K. So if it's a 90-degree angle, I know that from the previous table, the K value is 1. So substitute in the variables where Ri is 0.25 plus the material thickness 0.064 times 1. In this case, my setback actually distance measured will be 0.314 inch. Now, of course, over here, if the angle is larger or smaller than 90 degree, in this case, the angle of bend is 135. What do you mean by that? Please take note, bend angle is 45. And the other side of the angle is known as open angle, which is also angle of bend, which is 135 degree. So the bend angle required is 45 in this case. That means we want the sheet metal to be bent onto 45 degree, which is the bend angle. Please don't confuse. All right, 45 degrees. So my K is actually from the table itself is 0.4142. Right? So 0.4142 is from the table itself, the K charge table. So I substitute in all the variables. My setback actually required 0.13 inch. So this is the setback that I need 0.13 inch. All right. So I give you some time to read through these slides. Then I'll move on. All right. So quite standard. It depends on the bend angle. I say again, the bend angle that you want or the question asked. So what happens if you do not have a K chart table to refer to? Well, you can use trigonometric methods, okay, to solve this problem. Okay, using this as an example. Now, this is the bend angle of 45. So my angle of bend is 135. All right, so stated here, bend angle 45 degree. Angle of bend is 135. So add is 180 degree, right? Max, huh? All right, so half of the angle of bend is 67.5. 135 divided by 2 is 67.5. So this gives me the angle I have. And if I will plot a triangle, and of course, based on this angle here, the Ri plus T, this portion here is actually opposite. All right, opposite. Then adjacent will be my setback. So using that will be tangent. So tangent to Akaso, right? Tangent 67.5 degree is equal to Ri plus T, right? Correct. This is my bend radius. You see, from here, this point to my distance travel here, this is bend radius, the bend radius, right? And plus the material thickness, this will give me my distance, which is known in this case. Okay, 0.25. Earlier question is 0.25. Bend radius plus 0.064. This will give me the distance here. So with the given angle, given distance of opposite, then I should be able to calculate my setback. So and here you are. The setback is 0.13 inch. as per what we shown earlier using the K chart of 45 degree. All right. So yeah, let's move on then. If you have another few more seconds for you to run through and better understanding. All right. So let's say your angle is in this case more than 90 degree. So it's quite similar. Okay, if the band angle is more than 90 degree, in this case maybe 120, 135, I'm not sure, it's not stated. So what you can do is 180 minus away the band angle will get you the remaining angle of band. You should be divided by 2, then where you get, do take note, is depends on where your angles are formed, and the distance here you know, right? The band radius plus material thickness, then this is my setback. So you can have the calculation based on mathematics approach rather than using a chart to refer. Okay, I'll give you a few moments to look through this slide before I move on. Okay, this is another example for us to better understanding calculation of setback using the chart or without the chart. So in this case, okay, the angle of band is 45. So the band angle in this case is 135. All right, so that means you want to have a band angle of 135. Right. So using the setback calculation table and formula, from the table itself, I know the K value is 2.4142. Okay, this is from the table. If the table is available, you can refer to your notes. All right. So you substitute in all the variables, you will get your setback of 0.758 inch. So below here is actually using the trigonometric method approach to solve and get the setback. So in this case, if you punch in all the calculations, you will get 0.758 inch also. I think the next slide is actually working, which is much more clearer in this case. Okay, I'll give you a few moments to see through this calculation. Okay, so let's move on. If let's say we would need to bend a U channel, in this case as shown here, okay, a U channel, and the material thickness is 0.064 inch, right? And the band radius given is 0.25 inch, which is what they call typical band radius available. So both sides using the same band radius with a U channel, and the form dimension of the U channel should be 2 inch each. That means if you do measure, it should 2 inch. You do take note that the 2 inch are actually overlapping each other. Can you see that? It includes the material thickness and the band allowance while the setbacks are. So now, let's do a calculation first. What is needed? In this case, all right, I calculate my setback. So Ri plus T is given. Something is wrong. What is wrong? Can you think about it? Can you identify what is missing? Setback is Ri plus T. Is this formula correct? In this case, this calculation setback Ri plus T for this U channel, the setback calculation is correct because K is 1. 90 degree K is 1, right? So if 90 degree K is 1, so they just did not put in the K value. So Ri plus T times 1 is equal to that value. So 0.25 plus 0.064 inch, it will give you 0.314 inches. 0.314 inches is the setback, you can see. So how do I calculate my flat A? So in order to get my distance of flat A, I know my overall distance is 2, so I minus away my setback, I will get my flat A measurement. So 2 minus 0.314 is 1.69 inch. So my flat A and actually flat C share the same value. Now, the only thing to take note is flat B. In order to know the distance of flat B is actually 2 setback. You have to minus away 2 setback. You look carefully, 2 minus 1 setback here and 1 setback here will give you the distance of flat B. So it's 1.37. Alright, then how do I calculate my band allowance? It's 0.44 per band. How do I calculate it? Let's see the next slide. Did you mention about that? Right. So previous slides we had already obtained or calculated the band allowance, setback, and the measurement of flat A, flat B, and flat C. So with all this necessary data, we can actually mark out through the flat sheet and carry out the banding to form the U channel. Right. So before we move on further, band allowance we obtained is 0.44 in earlier slide and never show the workings. So there are two methods to obtain the band allowance. In this case, you can use the band allowance table provided in your notes based on the material thickness, all right, and the band radius used. If not, you can use the formula given, band allowance. Please remember this formula. You will be not provided for your test. Okay, it's actually your band angle. Okay, band angle. In this case, the band angle is 90 degree divided by 360. You multiply 2 pi. Okay, multiply 2 pi, open bracket. Then what is the band radius? Okay, in this case, the band radius will be 0.25. And then in this case, to make life easy, I use 0.5 material thickness, half of material thickness in this case, I consider. The range is 0.445 to 0.5. So we can use 0.447 times material thickness, up to you. Yeah, it's a try and trial method. All right. So using this formula, band allowance, all right, you should be able to calculate it and obtain the value. Then you mark up. So how do I get 1.69? It's actually, in fact, the overall length, true in this case, minus away the setback will give me 1.69. So this measurement from the edge of the sheet metal to the first line that you draw on the metal will be the first band tangent line. And from there, you would know that 0.44 band allowance, that's your second band tangent line. Then 1.37 is flat B dimension, and so on and so forth. If you add up all the dimensions measurements, you realize that your overall line is 5.63, slightly shorter than the required 2 inch, 2 inch, and 2 inch. If you add up, it's 6 inches. All right. So we will explain more on marking out during our practical session. You will have better understanding. But one thing to take note is when we do a mark out, especially on the sheet metal, we do not directly using a pencil to draw on the metal surface because pencil itself contains graphite and it will introduce possible corrosion development subsequently. Right, so normally what we will do is actually use a masking tape to take over the surface and draw the marking. Then we also don't use a scribble to scratch onto the metal surface because it will introduce scratches and lead to corrosion in the finishing part. Right. Okay. So yeah. I give you a few moments before I move to next slide. Before we move on, do take note that actually there's a sideline. The sideline is to tell you where do you insert your metal piece until, okay, in for the pen and box bending machine. All right. So again, these slides actually shows you the possible sideline. Okay, sideline is the one that you use to gauge and bend the sheet metal to form the required angle. In this case, there are two methods here. One is using the setback, which is R, bend radius plus thickness. All right, the other one is directly just using the bend radius. There's no, it's preference. All right, it's preference. It depends on the setup of your pen and box machine. It's a setup. All right. So this will further explain during our practical session. It's not that easy to explain over PowerPoint slides. All right. So during practical session, we will talk more about sideline and marking out. All right, relief hole. Relief hole is we use relief hole to allow the metal to flow at the corner during bending. All right, if not, it will crumple up. So what is the diameter of the relief hole? The recommended relief hole radius is 2 to 4 times the thickness. Take note, thickness is the radius. So you multiply, let's say example, the thickness is 0.5, 0.5, okay, 0.5 is a bit too thick, 0.05. So you multiply by 2 is 0.1. So 0.1 is the radius. You multiply by 2 is 0.2 inch. So you find something that is 0.2 inch diameter. Drill bit. So to drill this. All right. To take note. So these are now some samples on the relief hole. Okay, we will do a relief hole during our practical also when we bend our bracket. All right. So the difficult part about bending sheet metal is the amount of spring back effect. It's not that easy, especially we have various series of aluminum alloy 2024, 7075, 5056, or even pure aluminum 1100. I would say sheet metal bending is a bit of art, judgment, accuracy, and skill. Saying that you have a very accurate calculation, you can mark out accurately, but when your judgment of sideline placement and bending will affect your overall completion of the bracket or the channel you want to form. All right, so all this takes in a bit of work experience and more practices to make it perfect. So the variables that affecting spring back are thickness of the stock material, okay, type and condition of stock material. That means is it a zero original condition, a tempered condition, is it a 2024, or is it a 1100 series? What is the bend radius used? The bend angle you want to achieve, and followed by the shape and profile of the parts you want to form. All right. So this will be the practical work that you will need to complete during the practical session. It's very interesting. You will see some will achieve a perfect bracket measurement. Some will some measurement will be out. So it's very interesting to look at how things will develop when doing the practical part. Then of course, just take note of this is before fitting onto the aircraft, after you bend the sheet metal, the parts are actually painted and the paint is causing chromate. All right. So I think this should be end of our one. So okay, before we go, do you know what these machines or tools are used for? This is the pen and box, which I refer to. The pen and box. Okay, all these are available in our sheet metal lab, and we will go through this during our practical.